Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is best node, and it is a medium level problem. So the problem statement says that we have been given a tree and it will be given in the input format such that there will be an array, and at each index the array of I denotes that this is the parent of that particular element. For example, this is the parent array. Now at index 1 or the starting position, it is -1, that means it is the root node. At index 2 it is written 1, that means 1 is the parent of 2. Similarly at index 3 it is also written 1, that means 1 is the parent of 3, right? So this is the parent array that has been given to us in the input. Now there is one more array called the value array. Now this particular array has some values written in it, and these values will be the values associated with that particular node. Now we can start from any of those nodes. We can just choose any of those nodes and we have to go to any one of the leaf nodes, right? Remember these two things, we can go to any one of the leaf nodes and it should be a leaf node, right? These are the two important properties. First of all, you have to start from any node and then you have to go to any of the leaf nodes. Now you have to go in such a way that like at every node you visit, you will have to form this kind of sequence. So b1 is the value present at the first node, b1 is the value present at the second node, p3 is the value present at the third node. What you have to do is you have to form this kind of series where the first value is taken as it is, the second value is taken as a negative, the third value is taken as it is, the fourth value is taken as negative, right? By negative I mean you have to multiply the value by -1, right? So if it is already negative, you will have to make it positive, right? So we have to add all the values in that particular series in this particular manner, and we have to find the maximum possible value of f of b. So f of b would be the maximum possible value you can form by choosing any start node and going to any end node from that particular node. And remember, you can only go to the children of the particular node. You cannot travel back to the parent, right? So this would be the problem for today's Geeks for Geeks problem of the day. Now let me just explain you the problem here also. So if this is the first node and this is the second node and this is the third node, what you essentially have to do is you will have to, for example, these are the values. Here the value is 1, here the value is 2, here the value is 3, right? What you can do is you can choose this as the starting node, or you can choose this as the starting node, or this as the starting node, right? You can choose any of them. But in this particular case, choosing this particular node as the starting node would be the best case scenario, because it will help us to maximize the answer. Because if you start from here, this is only the leaf node, so you don't have to travel here, so the answer would be 3, right? So let me just give you a better example. So this is the sample test case that is given to us. Now in this particular problem, you can check and verify all the answers, but I am just going to discuss the best possible answer in this particular scenario. So the best possible answer would be to start from this particular position, right? So from the first position, what we'll have to do is we'll have to take its value, which is 7. Now the second value is -40, so you will have to add it, because -4, it will be something like this, -40, right? So this is actually equals to 21. Now in 21 you have to subtract 3. 21 minus 3 is equals to 18. So you have got 18 here. Now 18 plus 14 again you will have to do. So it will be 32 plus 14. It will be equals to 32. Then minus 12. After doing minus 12, you will have got 20, and then again plus 6, you will got 26. So 26 is the best answer you can form in this particular test case, and the path would be starting from 2, then 3, 3, then 4. From 4 you can go to 5, 5 go to 6, and 6 go to 8, right? So this would be the best possible answer. Now in this particular problem, what we can do is we can divide the problem into two halves. So for example, for each node, it can be part of at most two types, right? So for example, it can contribute its own value, or it can contribute its negative value. Negative value, by negative value I mean its original value into -1, right? So it can contribute, any node can contribute to the final answer in these two ways, right? Now if it can contribute in these two ways, then we have to find the maximum answer considering all the nodes can contribute in these two ways, right? So for example, if one node is a parent of this particular node and its contribution in the final answer is negative, so its child's contribution should be positive. But if the node's contribution was positive, then its child contribution should be negative. So it somewhat forms like a classical DP problem, what we have already seen many times while solving dynamic programming problems, where each state has like two values, and its previous state also has two values, its previous state also has two values. If we have taken this particular thing at this place, we have to choose the other one, and then we have to choose the other one, right? So these kind of problems are very common in dynamic programming, and this problem somewhat resolves that particular problem. Now there is one very important thing that I want you to know, and it will help you save a lot of time while solving problems. We have to, like, before even starting with a DP solution, we have to consider the data structure that is being used here. So if you see that we have been given a tree, right? So the tree would have any structure like this, right? So if we are given a tree, you would all observe, this is not a graph, this is a tree. You would observe that every node n is visited at most once, right? Every node is visited only once, and no nodes are revisited. Like, unlike a graph where every node can be revisited, it cannot be done in a tree, because if you go from the root node, you can only go to its child, right? And from the child, you can only go to its children. For every node, you will observe that the in degree is always 1. So if you talk about any node, you can always visit it once. Dynamic programming is only helpful when there are some overlapping states or there are some overlapping subproblems. But here you will observe that all the problems are not overlapping, right? All the problems are already in a simple manner, and every problem or every sub problem will only be encountered once. So the first thing that we have realized is that dynamic programming is not at all needed. However, the idea can be taken from dynamic programming, because we have solved many similar problems like this. But since the problems will not be overlapping, dynamic programming is not actually needed, right? We don't need the memorization part of dynamic programming. So this is the first important observation about this question, right? So after this is resolved, now the second question is, like, obviously you would have to traverse all the nodes in some or the other way to solve this problem, right? This is for sure. Now the question is whether we should go from top to down or bottom to up, right? So in this particular case, going bottom to up has its own disadvantages. I'll discuss why. So for example, during bottom up, we will have to, like, in some way consider starting from the leaf nodes, right? Because if you are doing from the bottom up traversal, you will have to start from the leaf nodes. But here you will observe that the answer for any node depends on its children nodes, right? So for example, if you started your traversal from this node and then you went to this node, right? But this node's answer cannot be calculated yet, because this node has not been evaluated yet completely. Because, like, for example, in the first iteration, in the first level of traversal, you have computed the answer for this node and you have computed the answer for this node, right? Now you want to compute for this and this, right? You can compute for this one because all its children have already been computed, but you cannot compute for this one because all its children have not been computed yet. So what we'll have to do is we will have to maintain an additional data structure like a priority queue or something, which will, like, just increase the time complexity of our problem, right? We'll have to maintain an additional data structure to make sure that the nodes with all the children computed are computed first, and these nodes are left for later, right? We'll have to maintain this in a separate fashion. So the only approach we are left with is the top to down approach, without any dynamic programming, without any extra stuff. It's just simple DFS. Now how we will compute the answer, right? Let us discuss that. So let us first form the base case for every of the leaf nodes. For example, these are the leaf nodes. The answer for this particular node can be either a of I, which is given in the input, right, or minus a of I, right? It can contribute in these two ways, right? So why not store both of them? Let's say, for example, for this node, I store a of I and I also store minus a of I. Let us just store it in a pair. I do this similarly for this particular node and this particular node as well. Right. Now, for the parent, what I will do is, if I am taking minus a of I here, I'll consider its a of I and its a of I. Right. If I'm considering positive a of I here, I'll consider its minus a of I and its minus a of I. Right. So what I have to do is, I have to start from the root node. I have to calculate the answer for its children. Right. At any of the nodes, for example, if I am taking the first value, then the answer will be a of I plus negative of a of j. Let us take this, where j are all the children, right? We have to take the maximum value among all the children, right? So if a of I is the node and if I is the node and j are its children, we have to take the maximum value of this expression among all its children. Similarly, if we are taking the negative value here, if I am taking minus a of I here, then I'll have to take plus a of j. Now j is children, j can be any children. We have to take the maximum value among all its children, right? And we have already discussed the base case. In the base case, the value will be itself a of I and minus a of I. We don't have to talk about its children because there aren't any, right? So we have discussed the general case, we have discussed the base case. Now how we will form the final answer? There is a simple constraint while forming the final answer, and that is the first value is always positive, right? The series is like this: plus 1 minus 1 plus 1 minus 1, or plus x, you can take any integer. So the first number, if you observe, is always positive. So this is also very one important thing. Now while considering the answer for every node, for example, you decide that you start from this particular xth node. Now for this xth node, you have to consider this for the final answer. You cannot consider this one as the final answer. Why? Because the first element is always positive, right? So we'll only have to consider the positive part as a candidate of our final answer. Now this was all about the approach for this particular question. Now let me just quickly recap the approach once again. So we have discussed in this particular problem, this particular problem resolves somewhat like all dynamic programming. It's very similar to many of the DP problems that we have solved, but we'll not use DP here. The answer is very simple, because it is a tree and every node will only be visited once, and there are no overlapping subproblems, right? So we don't have to use dynamic programming. Now why don't we use bottom up approach? We don't use bottom up approach because there might be many cases like this, where the children of a particular node has not been already computed, but it is ready to be executed, and its children are not yet written, right? So that means we cannot take this approach as well, because now we will have to maintain an extra data structure just to make sure that the children are computed before the node is computed, right? So the only approach left is top down approach, where we start from the root node and we just traverse through all the tree. Now for the base cases for the leaf nodes, we have decided the value should be a of I and minus a of I. In any general case, the answer would be maximum of all these values among all the children of the ith node. Let us say their children are j, so we have to compute all the values among all its j children, and if we take the positive value here, we have to take minus value from its children. If we have taken my negative value here, we have to take positive value from its children, right? So this is how we'll compute both the positive and the negative values for each and every node. Now while considering the final answer, we cannot consider the negative value. Why? Because the series itself starts with a positive value, so we cannot consider the negative values, right? So at the end, we have to consider the positive value of all the nodes present in the tree, right? Now let me just show you the code. So the code is not very difficult. What I've done is, here is the main function. So I have initialized a vector. I've created the tree in an adjacency list kind of form. So for every node, what I do is, so this is the parent. I just push the child into the parent, and I'm used zero based indexing. That is why I've done -1 here. So I've initialized my final answer with minus 10 to the power 9. So I've done this because I've taken it here as a global variable. So I just initialize this here, and after that I call my DFS function, where I pass my current node, my tree, and my array A. So in the DFS function, what I do is I initialize the value of x and y as 0. So x will store the value when we consider the current node's positive value, and y will store the value when we consider the current node's negative value. So if it is a leaf node, that will be symbolized when the current node's size is 0. There are no children for the current node. So when it is true, what we'll do is we'll just initialize with its own value, right? X will be the positive value, y will be the negative value. Now for every child of the current node, what we'll do is we'll just call the DFS function again, and we'll receive two values. So the first value of the pair will have the positive value, and the second value of the pair will have the negative value. So x is equals to max of x comma a of node plus answer of second. Right here, I'm taking the positive value from a of node and the negative value from its children. Right. Similarly, y is equals to max of y comma. Now again, I'm taking the negative value from the current node and the positive value from the child node. So this is first, which will be the positive value. I set my final answer as maximum of final answer comma x. So remember, I told about I will be already taking the positive value for considering the final answer. That is why I have taken x here. At the end, I can just return the pair x comma y. So after all this DFS is done, at the end, I'll just return my final answer. So this will be the solution for today's problem of the day, that is best node. I hope you guys were able to understand the solutions. If you did, like, you can show your appreciation by clicking on the like button. You can also subscribe to this channel. It's always free of cost, and don't forget to share this channel with your friends. So till the next video drops, keep coding, stay safe, bye bye.